Hello everyone and welcome to this video session on the thermodynamics. This particular video lecture is going to be one of the most important because we are going to look at the first law of thermodynamics, its mathematical formulations, various conditions and further limitations. So, when we are speaking about the first law of thermodynamics, okay, now this particular first law of thermodynamics was been put further, it was been proposed by two scientists, namely Robert Mayer and Helmholtz. Okay, so these were the two scientists who collectively put further their statements on the first law of thermodynamics. So in order to understand this particular first law of thermodynamics, first let us say that we are going to take into consideration of a system. Now please make sure that you understand the different types of system before coming to this particular process. So we have different types of systems. I hope you remember that there is an open type of system, closed type of system, isolated system. Correct. So here we are going to take into consideration of an isolated system. Let's say that this is our isolated system here. So when there is an isolated system, what they say is, in this particular system, any process which is occurring, okay, the energy of this particular system remains constant. So in short, they have put further a statement which says that the energy of an isolated system remains constant. Now, what does this particular thing mean? That whenever we have a system, and if particular this system cannot exchange heat with its surroundings, that time this energy remains constant. Or in other terms, they put further as the energy can neither be created nor be destroyed, but it can be transferred from the one form to another. Okay, so this is the statement of our first law of thermodynamics. Either you can go with the first one, that is the energy of an isolated system remains constant, or you can go with the second one wherein it says that the energy which is involved in a process, this energy can neither be created nor be destroyed, but yes, it can be transferred from one form to the another form. Now, hence this particular law is also called as the law of conservation of energy. Okay. Now, in order to understand about this, okay, let us say that we have this particular system. Let's say any system we are going to take into consideration. Okay, let us say this is a system as what we have, and let's say to this system we are going to use a piston. Let us say this is the position of the piston and which is attached at this point. Okay. Now, let us say that in this particular region of cylinder, we have certain amount of gas that has been taken. Okay. Now, in order to understand about this particular first law of thermodynamics and how it has a relationship with our previous concept of internal energy, you need to observe this particular condition very well. Suppose this is a system where it has a piston fitted to it. Okay. Now here we are going to supply certain amount of heat energy to the system. Let us denote the heat as Q. Okay. At the same time, let us say that we are going to work on the system. That is, you are going to pressurize this particular piston. You are going to pressurize it. You are working on the system at this particular point. Now, what is going to happen when we work on the system and when we are supplying heat to this particular system? There is going to be the change in internal energy. Okay. Now, if I am saying that there is a change in internal energy, that means it should be given as delta of U. Okay. Now, this internal energy, change in internal energy is equal to Q, that is how much amount of heat I have supplied, and plus it is going to be a work done, but this work is of the product of pressure and the change in the volume. Okay, so Q plus delta P delta V. Okay, so this is our mathematical formulation. Or I can also give it as simple as, quite simple as, delta U is equal to Q plus of W. You can either choose any one of these. Okay. So this one is our expression for the first law of thermodynamics. That is, the change in the internal energy is equal to the heat supplied plus the work done. What kind of work it was being done on the system was a particular product of pressure and change in volume. In order to proceed with the next conditions with respect to this first law of thermodynamics, let us first write down the equation for the first law of thermodynamics, and that was the delta U is equal to Q plus W. This is what we had arrived at. Correct. Now, there are four conditions, or you can say there will be four cases which we are going to study step by step. Okay, the first step or the first case number one. Case number one, in the case of isothermal process. Okay, now first let's study what will happen to the same system when that particular system is going to work at an isothermal condition. Iso refers to constant temperatures. So when there is no fluctuation, when there is no change with respect to the temperature, it has a direct influence on its internal energy. So when it is a constant temperature, so therefore at isothermal condition, okay, so at the isothermal condition, what will happen is delta U is going to be as equal to 0. So what does this mean is that Q plus W is going to be equal to 0. So again, I can have two conclusions from this. Correct. So let's say that Q is equal to minus of W. Correct. Now, they are speaking with respect to the heat transferred to the system and the work done. Correct. Now it is minus W. Minus of W refers to that the work is done by the system. Okay. Of course, we can also write it as W is equal to minus of Q. Okay. Even that thing we can take into consideration. But right now, we'll just speak with respect to the work which is done in a reversible condition. If we remember the entire equation for the work done in the reversible process, that is going to be equal to minus of 2.303 into nRT log of V of final state volume of initial state. This was what condition we had. Correct. So therefore, now Q is equal to, now minus of minus over here, again it is going to become as 2.303 nRT log of Vf over Vi. Correct. Now this is the amount of heat, when we are supplying to the system which is undergoing a reversible work. Okay, so this is for the reversible. So this is for the reversible work which is going to be done. Okay, now in case if we are speaking about irreversible process, so for an irreversible work, what happens is this expression changes as simply as Q is equal to, okay, minus of this one, that is minus of Pex into Vf minus of Vi. This is what expression becomes if we have a particular process which is undergoing a reversible work, which is undergoing a irreversible work. Now, getting back to the first stream, let's understand these two conditions. That is, it can be Q is equal to minus of W, or I can write it down as W is equal to minus of Q. Let's understand this in a very simple manner. Okay, so if they are saying like Q is equal to minus W, what is Q? Heat transfer. W is work, correct. Now, we have spoken about the work influence on the system. If the work is done by the system, the work is taken as a negative. If the work is done on the system, the work is taken as to be positive. So at an isothermal condition, remember this point, at an isothermal condition, this particular condition, if you are supplying heat, okay, the temperature of the system is constant, and now at this particular point, if you supply heat, the work will be done by the system. Let's try and understand here. Okay, so if this is a system, let's say this is a system as what we are speaking, and let us say this is the position of the piston that what we have here. Okay, so these are the gas molecules, let's say. So right now I am taking this particular system and I am keeping it at a room temperature. So temperature of room is constant, correct? So at this point, if I start giving this particular system certain amount of heat energy, what will happen? The molecules will absorb that heat energy. They will start moving with a higher speed. As they start moving with a higher kinetic energy, of course, they are going to produce pressure. As they produce pressure, this particular piston slowly moves. That time the work is done by the system. Understanding? So this is saying that when you supply heat at a constant temperature, the work will be done by the system. Reverse the process. What is the reverse of this particular process? I am going to take this particular system here. Okay, and let's say this is the position of the piston. These are the gas molecules, and let us say that this system is kept at a normal temperature. So now, what will happen is if I start working, see here, if you see the work done is positive, that means we are working on a system. If we are going to work on a system by pressurizing this, what it says is minus of Q. What is meaning of minus Q? It refers that the heat is going to be liberated. That means system loses heat. That time heat is going to come out of this particular system. This is how the relation is. Okay, so I hope you have understood these two conditions. But these two conditions are occurring as a case of an isothermal process. Okay, so this was our first case. So in the first case, isothermal process, delta U, change in internal energy becomes equal to 0. Let's go with the second case. Our second case is that when, that is case number 2, when work done itself, when the work done is equal to 0. Okay, so from this expression, first we have taken as delta U. What happens when it becomes equal to 0? Now we are saying that what will happen if the work is 0. Alright, so if the work done is 0, that is W over here is equal to 0. Okay, so what we have? We have the expression that is delta U is equal to Q, right? So what it says is, at this particular condition, when there is no work done in a sense, the volume of the system remains constant, correct? So when we supply the heat, okay, so at the constant volume, the heat supplied, okay, so we are going to supply the heat, so heat supplied to the system, it directly influences its internal energy. That means it increases the internal energy. So therefore, increases internal energy. So what is the condition here? The condition is the constant volume, correct? So therefore, we can also write this down as delta U is equal to Q. Q is the heat supplied to the system, but at the constant volume. Remember this point, okay? So these points are very, very crucial, very important, you see. So such kind of Q is equal to minus of W, W is equal to minus of Q, when it happens, how it happens. So all these are logical points, what we have to remember. Okay, so now, going further. So this was our case number 2. Going forward with the case number 3. So case number 3 is nothing more than when Q is equal to 0. That means you are not supplying the heat at all. Okay, or there is no exchange of heat. Okay, so let us put it into a very simple manner. When no exchange of heat occurs between the system and the surroundings. Okay, so try to understand, there is no exchange of heat itself between the system and the surrounding. There is no exchange of heat. So when there is no exchange of heat, I hope you remember that when there is a condition as such, when a system does not exchange heat, that is, the heat from the system does not go outside, or from the outside it cannot come inside. There is no exchange of heat. Now there, such kind of systems, the wall is considered as an adiabatic wall, correct? Now the processes inside, we call it as adiabatic process. Okay, so when it is an adiabatic process, the work done is called as an adiabatic work. So the work which is done at an adiabatic process also you can state it. So therefore, at this particular position, what we have, delta U is going to become equal to the work which is done. But the work at this point is done at an adiabatic process, so we will give it as ADI. Okay, so when it happens, you have understood that when there is no exchange of heat between the system and surrounding, this particular process turns out to be an adiabatic process. Okay, so these are the 3. We will see one more case. So let us begin with the 4th condition. In order to understand the 4th condition, let us say that there is a system, and this particular system has n number of moles of gas. Okay, let's take this as a condition over here, and let's say this is the position of the piston as what we have here. Okay, so this is the position of the piston. Now let's say that this is n number of moles of gas. Okay, so let's say these are n number of moles of gas. Okay. Now, as it is a gas molecule, the gas molecule has a certain amount of internal pressure. Correct. So let's say that the pressure that is present inside this particular system, let us give it as PRN. That is nothing more than the internal pressure of this particular system. Okay. So now, in case if the internal pressure is more than the external pressure, then what will happen is this piston will start moving slowly upwards. Do you agree with this particular fact? Correct. So when the piston moves upward, that means at this particular condition, the work is done by the system. Correct. So if the work is done by the system, here, can we take it down as work is negative? So, work is going to be negative. Correct. So, therefore, or can we write down this as or work is equal to minus of pressure into the change in the volume, because of course the volume is going to change. Okay. Once the work is either done on or by, there is change in the volume. Correct. So, now, if that is a condition, let's take this and let's substitute this condition. Substituting the work in the first law of thermodynamics expression. Okay. So, if we are going to do that, then what we have actually delta U is equal to Q plus of W. Correct. But W we have to substitute by this particular value. Therefore, what is going to happen? Delta U is equal to Q minus of P into delta V. Alright. So, this expression holds good when the work is done by the system or when the gases are expanding. Okay, so remember this point. So this expression is when the gases expand, or we can say that work is done by system. So when you have this particular expression can be used. Remember this point. Alright. Now, final point. That is nothing more than the limitations of this law. Okay. So, limitations. What this particular law says? That the energy can neither be created, neither it can be destroyed, but it can be transferred from one form to the another. That's all it says. It does not give us any account as the direction of the change, from what type of energy to which form it is changing. It does not give an account for that. It does not give an account to extent to which the energy forms are changing. Okay, for example, it does not give us whether heat energy is changing to mechanical energy or mechanical energy is changing to heat energy. It does not give us that direction. Okay, it does not explain. Second point is that it does not explain us how much amount of this heat energy has been transferred. Okay, so our first point that we need to understand is it gives no explanation with respect to the extent, with respect to the direction and extent of the energy from one form to another. So here is where it fails. The second point where it fails is that it does not give us any information with respect to how much amount of heat energy would be exchanged, how much amount of heat energy would be given up, how much amount of heat energy would be transferred from one form to the another. So it does not speak with respect to the heat energy. So gives no explanation. With respect to the heat transferred from one form to another. So that is it. Okay, so it fails with respect to the amount of heat transferred, and also it fails with respect to the direction and extent of the energy flow from the one form to the another form. Okay, so here we end with the first law of thermodynamics. So what are the important from the first law of thermodynamics is the first and foremost expression, that is the delta U is equal to Q plus W. Okay, keep that in mind. You can use this expression in the next lecture also. Stay tuned.